Thanks for the introduction, Sunshine, and thanks to all of you for your attention here. Before I begin, I just want to point out that the data and the information you're going to be seeing in this presentation is really the result of a long-term collaborative effort. There are several scientists at NOAA, both within my laboratory and others, who have spent decades studying the Great Lakes, and I need to acknowledge that a lot of their effort is put into the stuff you're going to see here. So to begin with, I want to give you a brief perspective on the Great Lakes and their magnitude in a way that impacts how we think about their water resources from a global perspective. I then want to talk about some specific examples of drivers of water quantity change in the Great Lakes, and then give a brief example of historical changes in water quantity looked at from the lens of water levels on the Great Lakes, really the best metric we have of the amount of water available in the lakes. And then give you a snapshot perspective on what we're looking at when we see projected changes in the climate and how those propagate into changes in the quantity of water in the Great Lakes. So to begin with, this slide shows an image of the Earth, and when we look at the Great Lakes from a water availability perspective, we can see the Great Lakes clearly here. You can see Lake Baikal, you can see some of the African Great Lakes. But I often choose to show this perspective, which is a summary of the largest freshwater bodies on Earth, ranked by surface area. So the first column on the left is the name of individual lakes, then the countries in which they reside, and then their magnitude both in terms of surface area and then in terms of volume. And I express it both in terms of standard international and also British units. And when I highlight the lakes that constitute the Great Lakes, we see some very interesting patterns, specifically related to water availability and water resources. One of the most important is that when it comes to surface area, there is nothing on Earth that comes anywhere close to the Great Lakes. Lake Michigan, Huron, and Lake Superior, as a minor side note, we often combine Lake Michigan and Huron as one large lake when we think of this as a large hydrologic system. Lake Michigan, Huron, and Lake Superior are the two largest lakes on Earth by far. And more importantly, when we think about the water resources that are made available from this system, they're directly impacted by the fact that we have this huge surface area. There's a lot of navigable water, there's a lot of water for drinking, and importantly, there's about 10,000 miles of coastline around the entire Great Lakes. That's greater than the U.S. Pacific coastline, that's greater than the U.S. Atlantic coastline, that's greater than the U.S. Gulf of Mexico. And all of that has implications for the type of water resources that we expect from this system. So when it comes to changes in the amount of water that's available in this system, what are the major drivers? And certainly this discussion starts and almost ends with the hydrologic cycle. Now this image is one I show often that shows the water budget of the Great Lakes. There are a lot of arrows coming into and going out of this system, but essentially we have a black line delineating the Great Lakes basin. And then we have a lot of these colored arrows, green, orange, and red, going into and out of each lake. And then the arrows in the middle sort of summarize what's happening there. Let me walk through those with you briefly here. First, I'm highlighting in green 3 arrows in the middle there that represent evapotranspiration, that is water leaving the surface of the Earth through both evaporation and transpiration by plants, as coupled with precipitation falling on the landscape. And together those two are what lead to runoff coming into the lakes through tributaries and streams. And there were some pretty amazing trends in evapotranspiration and precipitation relationships on the lakes. This particular slide that was published recently in the Journal of Hydrology by one of our postdoc fellows shows 4 important data sets for Lake Michigan. On the top row, you see the water level, the average annual water level on Lake Michigan. And for all these panels, a bar that is going up that is dark represents a year that is above average, and a bar going down represents a year below average. So what you can see when you look at water level dynamics on Lake Michigan is that there are times when we're above or below average, but that we've been in a period here for the past 15 years of below average water levels on Lake Michigan. And so the question is, why? How does that connect to precipitation and runoff patterns? Well, if you look at the next row in blue, you see patterns of precipitation, and what you might be able to see is that for the past 15 years, nearly every year in this region has been characterized by above average precipitation. So certainly precipitation alone is not a driver for water scarcity or low water levels in the region. Let's look at the next row here, which is represented by this variable Q. That represents the flow, the inflow of water coming into Lake Michigan. And now we start seeing differentiation between precipitation and flow patterns, namely Flow has been about average. It's been oscillating above and below average. This is flows coming into the lake. So the big question is, what is the relationship between the amount of water that has fallen on the watershed of Lake Michigan and the amount of water that's flown into Lake Michigan of that? And the last line answers that question, which is that the amount of precipitation, this last line is precipitation minus flow, and you can see that for the past 15 years, we've had a significant trend where a lot less water has been flowing into the lake coming out of precipitation. And we can attribute that largely to changes in that evapotranspiration, the amount of water moisture that is leaving the land surface and, following up on the previous question, leaving the snowpack before it has a chance to propagate into runoff. Okay, so next let's look at a couple other arrows here in the middle there. I'm highlighting this arrow on the right in orange to correspond with the orange arrows over each lake. That arrow represents precipitation falling directly on the surfaces of the lakes themselves. And I also want to highlight in red the arrow on the far left. That corresponds to each individual red arrow over each lake. That represents evaporation off the surfaces of the lakes. A take-home message for this discussion is that overlake precipitation and overlake evaporation, because the lakes are so massive, represent major components of the water budget. There's really no freshwater system on Earth for which that's the case, okay? Because essentially, the Great Lakes Basin is covered by about 30% water. So there's a question earlier about feedbacks and impacts on the water budget because of the lakes themselves. This is a tremendous part of the system, and one that we actually don't have a great understanding of. But let's walk through some of the phenomenon that we see and some of the impacts that are related to overlake processes. One, of course, is the relationship between surface water temperature, ice, and evaporation. This particular image comes from this past winter. I hope you can see it okay. In March, when we had an incredibly extensive areal extent of ice cover, not only on Lake Superior, but on Lake Michigan and Huron as well, going well into March. In fact, on Lake Superior, the official ice off date this winter was in early June. We don't have anything like that in the historical record. But what I want to talk about is the change in these overlake phenomenon as we go through the seasons. Here's an image from August of 2008. And what I'd like you to notice or appreciate is that if you look at the cloud cover over the lakes or around the lakes, you can see it almost looks like someone has taken a cookie cutter and cut out the cloud cover over the lakes themselves. Now that's a natural phenomenon where in the summertime we may have more condensation and less cloud cover of the lakes. But what we think has been happening is that there's been a positive feedback mechanism. We have evidence that there's less cloud cover over the lakes in the summertime over the past 15 years than we might otherwise expect, leading to a positive feedback mechanism where more solar radiation is getting to the lakes and keeping them warm. However, one of the caveats to that is there's not a lot of ways to monitor cloud cover out over the middle of the lakes. We have some isolated stations, but that's an important part of this story. And then last but not least, as we round through the seasons over the lakes, this is an image that I find pretty powerful of evaporation. In December of 2013, like other Decembers in the historical record, it's the peak of the evaporation season. It's the time when the lakes are still relatively warm, but we have cold, dry air coming in over the lakes, and there's a tremendous amount of water that's lost due to evaporation. A take-home message is that it's hard to understand these processes, as Don mentioned earlier, from models that don't include the lakes, these large climate models, and also from monitoring stations along the shoreline that don't necessarily represent the same information we're seeing over the surfaces of the lakes themselves. Okay, so what does this look like in terms of some of the data we've been collecting and implications for trends, variability, and regime shifts? Well, this slide shows Lake Superior surface water temperatures and ice cover. So on the x-axis along the bottom here, you can see years going back to 1970 or so. The red line is the annual average surface water temperature on Lake Superior. And you can see right around the late 1990s, there was a jump in Lake Superior surface water temperature and in Lake Michigan surface water temperature, but that's not on here, of about 2 degrees Celsius. A remarkable change that occurred. Incidentally, that was coincident with one of the strongest El Niños on record in the late 1990s. And there's a separate discussion we can have about attribution of that El Niño to this change. But one of the points of this slide is that the blue vertical bars you see represent the areal extent of ice cover each year, where as we progress through the year from bottom to top, you see I have days after November 1st. So December 1st, January 1st, March, April, May. The darker the blue, the greater the areal extent of ice cover on Lake Superior. So the dark blues represent close to 100% ice cover, and light blue or white represents no ice cover. So you can see, up until the late 1990s, you were pretty much guaranteed that you'd have some ice cover on Lake Superior, if not almost complete coverage for many of those winters. But then after the late 1990s, we entered a different regime where there might be years where you didn't have any ice cover on Lake Superior, or when you did, it very rarely would get over the full extent. And there's a very interesting discussion to be had here about trends, variability, and regime shifts. One of the most important is a differentiation between some summaries in the literature that say that there's been a trend in decreasing ice cover from, say, the 70s until present. One of the arguments I would make is that much of that decrease happened over the period of just 3 years in the late 1990s. And there's a similar argument that's been put out in the literature that says there's not really a trend. The best explanation for what happened here is you've got high ice cover until the late 1990s, a strong El Nino came along, and ice cover dropped. And that's an even better explanation for what's happening here. But then finally, if we add in data, of course, from this past winter, that changes the story yet again in terms of implications of variability. I've added in here the 2014 winter, where you can see a very early onset of ice, and of course, the late retreat of ice in June. And you can see also I've added in here a projection of the annual surface water temperature on Superior for 2014. The suggestion here is that it's possible we may dip back into surface water temperatures, not just on Lake Superior, but on the other lakes as well, that are more indicative of this pre-late 90s period than what we've seen over the last 15 years. Okay. And this image comes from a paper that or a short piece we just published in EOS. And there's a very similar paper that's in press right now with Limnology and Oceanography, published by John Lenners and his graduate student Katie Van Cleve. All right, so let's take a quick snapshot here of how over the past century or so, these changes in drivers of water quantity have propagated into the changes in water quantity. And the best metric we have for this really are water levels of the Great Lakes. And we could look at those over a variety of different time scales. The one that I have time to focus on for right now are these decadal or century-long changes in water levels. So to do that, I've got a panel up on the screen here, or an image that has 4 different panels. The top one is for Lake Superior, the next one down Michigan Huron, then Lake Erie, and then Lake Ontario. And we're showing a time range here going back to the mid-1800s. That's when we have some of our first water level measurements. And what I'm going to add in here, and also within each panel, there's a range of surface water elevations. The key point is that the range within each one of those is the same. They both cover about 2 meters or 6 feet or so of elevation difference. So when I add in annual average water levels here, we see some interesting patterns. Okay, one of the most important is that there's an awful lot of variability, particularly on the Lake Michigan Huron system. We can see that Lake Michigan Huron can go up and down on the order of 4 to 6 feet just over the course of decades. So for example, I can highlight, this red line that I just added in represents the long-term average on each lake. So I can highlight a period here in the 1930s when we had extremely low water levels. Again, water levels very low in 1964. But then just over the period of 20 years, water levels, particularly on Lake Michigan Huron, rose by about 6 feet to where we had flooding and erosion problems in the mid-1980s. A take-home message from this slide is not just about the natural variability of water levels, but that we can attribute most of these changes to corresponding changes in regional precipitation patterns. The one change that does not relate well to changes just in precipitation is the one that occurred, I'm not highlighting here, but the drop that we saw in the late 1990s. And that drop we attribute more to dramatic changes in overlake evaporation that jumped up at a time that happened at the same time of that strong El Nino, and then the subsequent positive feedback loop we've seen for the past 15 years that kept water levels low, particularly as you can see on Lake Michigan and Huron, where they've been low for 15 years. Minor update to this that is not on this slide. This month is very, very likely to be the first month in 15 years that all of the Great Lakes will be at or above their long-term average for that month. And that's something that we didn't necessarily expect to see for a long, long time. And we can talk more later on about why we think that has happened. So finally, to wrap things up, to talk about how climate change impacts, and obviously the previous session did a great job of capturing the uncertainty in climate and how challenging it is to understand the climate system and to reflect that understanding in climate models. But let's look here at what happens when we propagate that climate understanding into models specifically for Great Lakes water quantity. So I've shown here a slide that shows that same historical record of water level information, but just for Lake Superior and Lake Michigan-Huron. And I want to use that as a context for actually bringing up an image that comes from a paper that Don wrote with Catherine Hayhoe several years ago that really served as a cornerstone for perceptions about water level change in the region. And what this slide shows is decadal water level projections from a particular climate scenario using a particular model, and it led to a perception that water levels in the Great Lakes are likely to have a significant decline over the next century. And there's two important points about this figure that I want to make. One is that you don't really get a feel, and this is at no fault of the authors, but more so how this figure was subsequently used in the popular media and with the general public. You don't get a sense of how that variability relates to the variability of the system over the previous century. Okay? And a second key point comes from a key sentence that was in here, which says that the scenarios that were run with less warming that are not shown on here indicate that water levels probably won't change that much. I view that as an important projection to be put along here. So with those two caveats in mind, let's use the historical record here and let's project that model simulation onto the historical record. So we have this high emission scenario from that paper, and we're now looking at these orange lines, which are the decadal projections from that paper, put within the context of the historical record. And then another thing we can do is add in more models that have been run, one of which came out at just the same time. Jim Angel and Ken Kunkel published a paper at almost the exact same time. They looked at a broader range, and I hope you guys can see those green bars on there. They looked at a broader range of climate simulations, put them through the same model, but you can see the variability here in future conditions. I can add in yet again a green line that you might be able to see, run by our colleagues in Environment Canada, Murray McKay and Frank Sigliniaks, that shows very little expected change in water levels. And then finally, I can add in projections from my colleague, NOAA Brent Lofgren. So one of the take-home messages here is that we can gain an awful lot of insight about what future conditions might be by understanding the different assumptions that went into these models, how they relate the relationships between evaporation and precipitation over the lakes, and importantly, what we found in this is that very subtle differences in how you represent an understanding of temperature changes on the landscape and evapotranspiration and precipitation on the lakes can lead to very divergent predictions of what water levels are likely to be in the future. And there's not a lot of conclusive, I don't like to use the word evidence with forecasts, but there's not a lot of conclusion on here about which direction water levels might go in the future. Okay, so to wrap things up, I've argued here, and I think there's a lot of evidence, that precipitation and evaporation drive water quantity. Why do I point this out? Because there's a lot of confusion in the general public right now about the effect of water diversions out of the Great Lakes Basin, about the effects of dredging, and I want to point out very clearly that precipitation and evaporation are what drive major water level changes in the region, and that the other factors, these interbasin diversions, are orders of magnitude less than the changes I'm talking about here. However, in the future, there are stressors on the system that we might not be able to anticipate. One that we're working on are changes in human population and migration patterns and changes in water demand. Right now, water demand does not represent a major driver of water level change in the system, but it could over the next 20 to 50 or 100 years. And I think that's an important caveat to that point. Second of all, when it comes to managing water resources, I think it's important to recognize that there may be changes in trends, long-term variability, that have important implications for water resources management planning. And specifically, I'd argue that a net decrease in water levels of a foot over the next century might not mean much to a water resources management planner, someone who has a water intake pipe. But a dramatic drop of 5 feet over the course of 2 years may mean a lot. And there's an important connection there with trends and variability. I argue that when we're talking about this system, let's use data when we talk about evidence for something. And to borrow a term from our colleague Brad Udall out in Colorado, let's use forecasts and projections to gain insight about a system. And then last but not least, I'm happy to talk more with anyone in the room here or afterwards, but there are also some contacts at NOAA if you have questions about the Great Lakes. Monica Allen is our press contact at NOAA headquarters, and Margaret Lansing is the press coordinator and communication and outreach specialist for our lab in Ann Arbor. Many thanks to the folks here, and we have some agencies I'll leave up on the screen. That ends this portion of my talk, so thank you.